Good afternoon, everybody. So I will close this section about magnetic sensors by discussing some bricks that we are trying to put together in order to optimize the performance of the type of magnetometers that hasn't been discussed yet. It's Lorentz-Force MEMS magnetometer, work in collaboration between Politecnico and STMicroelectronics. The starting point for the talk and also the motivations lie in a table of the specifications of consumer-grade magnetometers. What is interesting to know that if you look for commercial products, you can find very different technologies for exactly Mark and TJ have seen during the former presentation, something about these technologies. All of these technologies, they have more or less, can reach more or less the same performance for consumer-grade sensors. Resolutions in the order of hundreds of nanotesla, with a full scale in the order of 1 millitesla, with a relatively limited bandwidth and low current consumption. The question can be, which of these technology is most suitable for next generation sensors where you want even lower resolution, have large bandwidth, and with an increased full scale range? And the second question is, can MEMS magnetometers be competitive with respect to these target parameters? And I'll start answering this question by looking at the operation of typical magnetometers, so what you can find more or less in almost all the publications in the scientific literature. As structures can be different, but the principle is basically described here. So you have a current which is injected into the springs that start the sustaining part of the structure. The current is typically injected at the resonance frequency of the device. So if we have a magnetic field in the outer plane direction, with the current in this direction at the resonance frequency, the device would experience a displacement in the horizontal direction, which is amplified by the quality factor. We can write also the thermomechanical intrinsic noise of the device, again in terms of displacement, starting from the Brownian motion integrated over the bandwidth of the magnetometer. Typically, this bandwidth is relatively small for high values of the quality factor, so typically it is fully exploited, so you can integrate this term into the full minus to the mechanical bandwidth. If you take the signal-to-noise ratio and put it equal to 1, you can derive the minimum magnetic field. And what you will note is that once you fix, for instance, the specification for the maximum current, so the power consumption, and you have a specification for the bandwidth, then what you can, in principle, act on to reduce and improve your resolution is the damping coefficient. However, if you decrease the damping coefficient, you will also decrease your bandwidth, so it's hard to get an optimization of this kind of devices by using this ad-resonance approach. So what we have recently explored and proposed is an operation of resonance, somewhat inspired by the operation of gyroscopes in mismatched mode. So instead of, this is the transfer function of the device, this is the resonance mode. Instead of operating in this very narrow region at the resonance frequency where the minus 2 dB bandwidth is typically small in the order of 2 Hz for quality factors in the order of 1,000, we simply have a current injected with a split delta F with respect to the resonance frequency. This split can be in the order of 100 or a few hundred of Hertz. You clearly have a decrease in the gain with respect to operation at resonance, but you can still have an amplification with respect to the operation in DC by a factor, for instance, of 30 if the mismatch is in the order of 300 Hertz. So we call this an effective quality factor, so a residual amplification that you have even if you are mismatching. This amplification is not a function of a damping coefficient, which is incorrect. What you get is, so you pay in amplification, but you gain in bandwidth, because your bandwidth is extended to roughly 1/3 of this mismatch. So if the match is 300 Hertz, you have a bandwidth in the order of 100 Hertz. And in the end, you have eliminated the critical trade-off between bandwidth and resolution that we have seen in the previous slide. Besides, this region is more stable, so we will be likely to have a better stability to temperature variations, to process mismatches, and so on. If we look now at a minimum measurable field, therefore, while in the resonance case you have this trade-off, here you don't have this trade-off because the bandwidth here is typically, the mechanical bandwidth is much larger than what you require. You will have an electronic filtering bandwidth which is independent on the damping coefficient, so you can try to act on this guy here, on the D coefficient, in order to improve your resolution. Now the critical point is to improve the damping coefficient without losing in sensitivity. If, for instance, the device is supposed to be read out through capacitance, to capacitive readout, what you would like to have is a sensing mechanism that guarantees a large sensitivity to magnetic fields, still guaranteeing a low damping coefficient. So this is why an optimization of the sensing electrode is required, and will be the topic of the next slide. Just a couple of quick notes. Typical operating pressures are in the order of 1 millibar or slightly lower, with gas in the order of 2 microns. So the Knudsen number, which is usually used to quantify the gas rarefaction, is typically larger than 10, which means that we are in a three-molecule flow regime, which in turn means that you can neglect molecule-to-molecule interaction. You can take into account only the interaction between the molecule and the walls of your moving device in order to calculate your damping coefficient. So with this assumption, with the assumption of the velocity of the magnetometer walls is typically smaller, much smaller than the velocity of the thermal molecular speed, and with another assumption that allows for a simplification of the description of the gas dynamics here, which is that the silicon surfaces are rough enough to allow a reflection boundary condition to be assumed like a perfect diffusion to an isotropic diffusion. By putting together all these configurations, we have implemented simulation tools that either based on stochastic approaches like Monte Carlo techniques, or directly based on the solution of the Boltzmann equations with suitable boundary conditions derived from all these configurations, allows you to estimate the quality factor even in the free molecule flow regime with a relatively good degree of approximation. So, with this in mind, what we now try to compare is the sensing, the differences in the sensing electrodes of a typical parallel plate differential parallel plate configuration. So suppose that the black beam here is moving in this direction, and you do the sensing with this kind of electrode on one side and with this kind of electrode on the other side. The two things that we have to verify are, first of all, that you do not pay too much in capacitance variation per unit displacement. So basically, you can, with any electrical simulator, do this kind of simulation, simulate the motion of the beam and the motion of the beam, and you calculate the capacitance variation for the two structures. And you can easily verify that basically the capacitance variation is more or less the same in the two situations. So you're not paying in terms of loss in capacitance variation per unit displacement. On the other side, the damping coefficient predicted by the technique described before can be 4 times lower or even more, depending here on the configuration of the holes with respect to the length of the existing part. Clearly, these are electrically connected by an interconnection that has behind all this area. For instance, with this approach for the structure that I'm going to see in the next slide, the predicted quality factor is in the order of 350 at 1 millibar, and then you will see it is proved by experiment. So the structure used for the test is schematically depicted here. You have a current entering the device injected at a frequency that we can select. It passes through this set of 9 springs. If you have a magnetic field in the outer spring direction, then you have a movement due to Lorentz-Force in this direction. And you can do the sensing with this kind of folded parallel plates that are sketched here in this optical picture. So first of all, we verified the results in terms of 40 factors, so checking the validity of our damping model using a system that we have been developing for 3 years in Politecnico as well, with good electromechanical characterization of capacitive MEMS, so the MEMS. Basically, you apply some square wave and you measure the downward step response. And for the device factors, 1 millibar we measure the factor in the order of 380, which is quite in line with the predictions, even slightly better. Then we had also the chance to test devices packaged at a lower pressure, roughly 0.2 to 0.3 millibar, where we found a Foley factor of 1300, 1400. With this device here, so with this kind of packaging, we went on with a measurement of the sensitivity to magnetic fields in different operating conditions. So we have in blue here the response in terms of voltage at the output power circuit with respect to the magnetic field on the x-axis, fully exploiting the Foley factor. And in these two further examples, we have the response when operating with an AC current which is not at the resonance frequency. In this case, we have a 100 Hz mismatch. In this case, a 300 Hz mismatch. So the sensitivity is effectively decreased by the factor which is theoretically predicted through the measurement confirmed effectively this amplification decrease, which is known. But what we gain is the maximum device bandwidth, which is extended from 7 Hz only when operating at resonance to 30 or 100 Hz in the two examples shown here. What we need to verify to conclude the things is that the resolution is basically, for the same bandwidth, is the same in the different modes of operation. So what we measured was the output noise of the system as a function of the modulation frequency, corresponding also to the actuation frequency chosen. You will see this kind of shape and for the noise which specifies the Brownian noise here. However, the noise floor of the electronics is still somewhat contributing to the overall noise when we operate with our mismatch, so that the measured noise floor is not exactly the same in the two conditions as expected. So basically, this is due to the resistance used to bias the charge amplifier that was used for the measurement of the setup. We're quite close to, with a slight improvement in the electronics, quite confident that we will come to the same value for these three modes of operation, with the benefit of having largely extended the bandwidth with these two modes of operation. So basically, we have put together operational resonance and the optimization of the damping coefficient, and we're working on the use of multiple thermal loops to recover somewhat the sensitivity that we have partly lost by operational resonance. And in parallel, we are studying and implementing an IC that goes with both with basically all the requirements that we have seen in the first table during this presentation. So the goal is to verify, and in principle we are there, that Lorentz-Force magnetometers can be competitive for state-of-the-art next generation of this program. That's all for this presentation. Thank you for staying until the last section.